Thank you, Umberto, and thank you to the conference organizers for the invitation to be here today. I'm really excited to join you, and thank you everyone for joining me. And as Umberto said, yes, heavy industry has been known for many years as difficult to abate, meaning there are many high temperature processes that are very fundamental to producing materials that are used in very large quantities around the world. And concrete, cement and concrete is one of those materials. In fact, concrete is the largest by volume, I believe, by mass even, material used by mankind, and it involves cement. And I'll talk today about technology prospects for decarbonizing this very crucial but yet very hard to abate material cycle globally. And I'd also like to acknowledge my co-author in the work, Dr. Zhe Chao. He's a colleague of mine at Northwestern University. I recently left Northwestern University to join the University of California, Santa Barbara. The work I'll present today was funded at Northwestern University, hence the Northwestern University logo. But Dr. Chao was instrumental, and I'd like to thank him right at the beginning for contributing to the work. And I'll use this somewhat obnoxious pointer, given that we're in a virtual environment. So let me start by introducing the term. What do I mean by the cement and concrete cycle? Well, when I refer to this cycle, I'm referring to what might be thought of as the life cycle of cement and concrete, starting back with mining operations for aggregates, rocks and sand used to make concrete, but also limestone, the primary ingredient in cement manufacturing. So we think of mining, we think of manufacturing the cement. The cement goes into concrete, which is a mixture of fine and coarse aggregates, water, and clearly cement. That concrete goes into the built environment where we construct our homes, our buildings, our roads, our bridges, and so forth. The use phase of concrete has, depending on the accounting methodology, very low or non-zero emissions. And then at the end of the life, clearly, after the built environment has reached the end of its useful life, it's demolished, and we can recycle concrete, or often we send concrete to low value applications like road filler and so forth. And overall, the cycle itself, let me just adjust my screen a bit here. The cycle itself accounts for about 3 gigatons of CO2 emissions annually. To put that into perspective, that's about 9% of total energy-related greenhouse gas emissions globally. So it has a pretty large share of emissions coming from the energy system. 3/4 of those emissions are attributable to cement manufacturing itself. That's why cement manufacturing has been the target of a lot of energy efficiency and increasingly decarbonization initiatives historically. But there are also significant emissions occurring during construction, pouring concrete, constructing the building. There are point source emissions across the cycle. And the other major contributor to this overall carbon footprint are the various transportation activities, particularly bringing raw materials from mines to the cement plants, but also shipping of concrete, shipping of cement, and then shipping of demolished building materials accounts for about 10% of the emissions of this cycle. So again, this cycle is one of the most important for well-being that we have because concrete is used everywhere in the built environments. It's crucial for development. It's crucial for daily life, and it amounts to 9% of energy-related CO2 emissions. And it's been very difficult to abate so far, and I'll explain why. But before I get into the decarbonization options, I'd like to acknowledge that the cement industry has made significant progress over the last few decades. So the first graph I'm showing you relates to the thermal intensity of cement kilns. So roughly 30 years ago, a ton of clinker. Clinker is the major cementitious ingredient that goes into cement. It's a material that's processed in the cement kiln at temperatures of greater than 900 degrees Celsius. And that energy intensive process uses a lot of fossil fuel presently, lots of energy, and relates to a lot of emissions. But there have been some tremendous efficiency gains that have been realized since roughly 30 years ago. 30 years ago, it took around 4,300 megajoules to process a ton of clinker. Today, that value is around 3,500. So we've seen energy efficiency gains through steady technology upgrades to the world's cement plants. At the same time, we've also seen a gradual increase in the usage of low carbon fuels in cement kilns. So what this graph shows is, compared to 1990, today we're much better at using biomass and other waste fuels that come with lower carbon footprints, overall reducing the carbon footprints of clinker manufacturing. So today, each ton of clinker globally, on average, uses about or releases about 800 kilograms of CO2, whereas roughly 30 years ago, that same ton of clinker required 900 kilograms of CO2 to be released to the environment. So that's more than a 10% decrease over time. So despite that really good progress that we're seeing in the industry, global climate ambitions require a really significant acceleration. So what I'm showing you here are recent results from the International Energy Agency. Energy Technology Perspectives 2020 is the most recent technology-rich report they've issued on global decarbonization pathways, and they have a strong focus on the industrial sector in the report. On the left hand, what you see is final energy use in the global industrial sector, including not just cement, but steel, chemicals, other industry. The blue dots show the so-called STEP scenario. This is the stated policy scenario. This is the pathway that the industrial sector is following based on existing policies and existing technology trends. The green dots show the IEA's sustainable development scenario. This is the scenario, this is the pathway that industry must follow in order to keep greenhouse gas emissions consistent with levels that will meet the goals of the Paris Agreement, specifically keeping long-term global warming to well under 2 degrees Celsius. On the right-hand side, we can see what this means for the emissions budgets for the various industrial sectors and for industry overall. And the key takeaway is, following the sustainable development scenario pathway, really all of global industry has to get very close to net zero emissions by mid to late century in order to meet the goals of the Paris Agreement, the cement industry included. And what you see here for cement, the yellow bars, the solid shade is the direct energy use emissions. The sort of hash shade here are so-called process emissions. These are CO2 emissions that come from the chemical reactions of making clinker, ordinary Portland cement clinker within the cement kiln. And these have been historically very difficult to abate because they're related to the actual chemistry of the material. So despite great progress, global climate ambitions are requiring a significant acceleration. And in the background, we also have growing demand for cement globally. So present day demand for cement is dominated by China. China produces more than half of global cement quantities. It's been that way for well over a decade now, or several decades in China. And the world consumes about 4 gigatons total of cement. Despite the fact that as economies develop, demand for building materials tends to become saturated, meaning we're no longer building massive new areas of buildings or roads, rather we're maintaining that built environment. We do expect that global cement demand will continue to increase through mid-century. So these are projections from my colleague Jia Chao at Northwestern, predicting roughly a 30% increase in cement demand through mid-century, largely fueled by development needs in Africa, in India, and developing Asia. And what we see in China is still significant cement demand, but it's smaller than it is in the present day because the built environment in China has become saturated. So this is an important backdrop. Not only do we have to reduce the emissions of the industry to near net zero by mid-century, we also have to do so while producing about a third more cement to meet the needs of a growing global population. And historically, most plans for the cement and concrete cycle have involved lots and lots of carbon capture. So for those of you who might not be familiar with carbon capture, it's a technology that will prevent emissions of CO2 from leaving the cement kiln and entering the environment. Rather than letting that CO2 go into the atmosphere, it's captured. Sometimes it's cleaned. It's pressurized, and it's generally sequestered permanently underground, either in depleted oil and gas fields or mineral formations and so forth. And there has been quite a bit of movement researching and developing carbon capture technologies that are applicable to the cement industry. And this is one example of a pilot project that's underway now, in place now, called Lilac. It's a calcium looping CCS technology, which is being pursued with funding from the European Union and also in partnership with Heidelberg Cement. These pilot facilities, at least one is in place and several others are in the works, are happening. But if we take a look at the left-hand graph, you quickly get a sense of just how important carbon capture is in many of the decarbonization plans to date. So what you're seeing here on the left is the amount of carbon capture that's necessary in the global cement industry in the IEA's ETP 2017 scenario. So this scenario was one of the very first to map out technology pathways for meeting the goals of the Paris Agreement. It's called the Beyond 2 Degrees scenario. The blue bars or blue columns here show the amount of CO2 that must be captured from cement plants in order to reach the goals of the B2DS scenario. That's nearly 2 gigatons by mid-century. And the red dots show the fraction of overall CO2 emissions that must be captured at all the world's cement plants. And here you can see it's over 75, close to 80%. So roughly what that means is 80% of the world's cement plants, well, actually more than that, because sometimes we can't capture 100% of the CO2. Nearly all of the cement plants globally by mid-century have to be equipped with carbon capture and storage under the sort of current regime of decarbonization plans. Technically, is that possible? Yes, it is. Like I said, the world is investing in CCS. Is it happening fast enough? My interpretation and the interpretation of many others is that no, carbon capture is not being rolled out fast enough in order to be on track to reach these levels of penetration by mid-century. On the right, what I'm showing you are recent data from the International Energy Agency. What you see here in these smaller column plots are the existing projects, large-scale projects of CCS globally. They include some industrial plants, mostly chemicals and steel, some biofuels, some refining, and most CCS capacity that's in place today is for natural gas processing. But just by looking at the sort of scale of where we are today and the projects that are in the pipeline, we can quickly compare to the amount of carbon that needs to be captured in the IEA Sustainable Development Scenario by 2030 and 2040. So we're an order of magnitude lower than the progress we need by 2030 presently, and 30 times lower than where we need to be by 2040. So the current trend line looks like this. We have to ratchet this up very drastically in order to have hopes of realizing visions like this. Technically, it is possible. With the right ambitions, it can be done. But what I'd like to do today is show you that the innovation landscape for the cement and concrete cycle is changing quite rapidly. And it is possible to reach net zero emissions without heavy reliance on CCS if we're able to accelerate the development and adoption of a portfolio of other technologies that are being pursued and piloted in different places around the world. So I will explain this graph a bit later, but what I'm going to do is use the example of China's building sector. So China's building sector is one of the largest end uses of concrete on the planet. Roughly half a gigaton of concrete or cement, presently goes into China's building sector. And we can reach net zero, and in this example in China's building sector, by pulling on a lot of emerging technology levers, accelerating them to market, ramping up their adoption such that we can reduce our reliance on CCS. And I'm going to show you how that can be done. But first, what I'd like to do is step you through some of the existing and emerging levers. So there really is a rich portfolio of measures beyond CCS that can help decarbonize the global cement and concrete cycle. Several of these are technologies that we have in hand. So the first one is somewhat obvious. I've talked about this already. This is improving the energy efficiency of cement kilns themselves. What you see on the right are data from the United States, the world's largest, third largest cement producer, but quite a bit lower, quite a bit smaller than the world's largest, which is China. But here in my country, we've been also making steady progress towards adopting more low carbon fuels and improving the efficiency of our cement kilns. But we're still quite a bit away from reaching global best in class values for kiln energy efficiency. So there is bandwidth to continue improving the energy efficiency of today's cement kilns, but it'll only take us so far. There's also been a lot of progress adopting more lower carbon fuels. So here's an example of a cement plant run by Lafarge in Canada, which is using large quantities of biomass, I believe baled hay or straw. So there is quite a bit of potential to just use more low carbon fuels, particularly biomass, in cement kilns themselves. But this technology is subject to the energy density of the available fuels. It's very difficult to run a cement kiln purely on biofuels alone due to energy density, but we also face potential issues of available supply in different parts of the world. Another key lever is just reducing the amount of clinker that goes into our cement mixes. So it is possible to manufacture cement with clinker mixed with clinker substitutes. The big ones are fly ash, limestone, blast furnace slag, gypsum, as you see here in this graph. And the world has been making progress towards using less carbon and energy intensive clinker in its cement blends and offsetting that material with much lower energy and carbon intensive materials like industrial byproducts like fly ash or simply ground limestone. And the technical potential for doing so is roughly about here. So we can make cement, and we are in many parts of the world, with clinker to cement ratios lower than 60%. But and when we do so, we substantially reduce the overall carbon footprint of cement. Those are measures that we have in hand. And as you can see from the various plots I'm showing you, we are making progress, but over the course of 30 years, that progress is pretty slow compared to where we need to go to get to net zero by mid-century. So we're starting to consider a lot of new measures. So there's been a lot of development in one particular category, which I'll call low energy, low carbon cement chemistries. So as I go through some of these emerging levers, I'll also give you an idea of what analysts think their TRL level is. This is the technology readiness level. It's a scale that's used often when classifying the availability or state of development of emerging technologies. And if you're not familiar with it, I've inserted this cartoon here just to give you a quick idea. So a TRL1 is initial conceptualization of a concept. TRL3 is proof of concept, going all the way through to TRL9, where it's basically available. It's in operation. It's available on the market. So low energy and low carbon cement chemistries seek to change the chemistry of the clinker material itself. And we want to do that because if we can do that, we can potentially avoid emitting CO2 during the chemical reactions necessary to manufacture clinker. One company that's already introduced its formulation onto the market is Solidia. There are a number of other formulations, and their availability ranges from fairly early proof of concept all the way through to market availability. But just to give you an idea of the concept, so if we use Solidia as an example, most of the carbon emissions from the chemistry of making clinker come from limestone, calcium carbonate. Solidia, the Solidia mix uses less calcium carbonate, therefore it has less of a lime content, meaning less CO2 is emitted during chemical reactions. It also comes with lower processing energy. So by kind of shifting the mineral composition in these low carbon cements, we're able to produce clinkers that emit less CO2 and ideally also just have lower energy requirements for processing. And there's a lot of innovation there. There's also been quite a bit of attention placed on replacing the existing kiln technologies, which are run largely on fossil fuels globally, with renewable or low carbon fuels. So in the IEA's Energy Technology Perspectives 2020, they have reviewed the state of different cement kiln technologies. And there are two major classes of alternative kiln technologies. One is running those kilns on renewable fuels. So the first class is direct electrification. Again, remember these kilns are running at 900 plus Celsius, so they're very high temperature. But there are pilot projects and projects underway to explore directly electrifying those kilns. And if we can do that, we can run them on renewable energy ideally, and therefore eliminate a substantial share of the emissions for producing clinker if they're being made based on, carbon-free energy. So there's been innovation looking at direct electrification of kilns, also using concentrated solar power and fluidized bed technology to use the thermal energy from the sun's rays to heat the mineral mix. There's also been attention being placed on the use of hydrogen. And if we can make hydrogen, green hydrogen from renewable energy and water, then we now have an energy carrier that can be used in many industrial processes, potentially also cement kilns. The key, though, is that these kiln technologies are all fairly low TRL levels presently. So it will be a while before we see these technologies being available on the market. And they also require having a renewable energy infrastructure and supply system in place in order for them to be successful. Moving on briefly, there's been a lot of attention placed on just reducing the overall amount of concrete we demand in our societies. So it's been recognized, I think, recently that, a very powerful mitigation opportunity with the industrial sector writ large is, can we simply produce less material, less goods, fewer products and so forth, so that we can, just need less of those things in the first place. And when it comes to concrete, there are lots of researchers looking into, well, how can we design buildings or building components that just use less concrete in the first place? For example, this is, I think, a well-known example that's being developed in ETH and EPFL in Switzerland, where it's a floor panel that uses roughly 50% less concrete because it has this unique design to it, which I believe was made by 3D printing. And if we can replace poured floors with panels that use 50% less concrete in buildings, now suddenly we've made a big step forward towards reducing the emissions of cement and concrete production simply by avoiding the use of concrete in the first place. And another key strategy that's emerging in many parts of the world is replacing concrete structures with cross-laminated timber. So this is an example of a building here in the United States in Portland. Cross-laminated timber has seen lots of innovations and improvements over the past few years. Now we're able to build taller and taller buildings using cross-laminated timber, which reduces the amount of concrete necessary in the structure, also ideally in the foundations and so forth. So simply using less concrete or replacing concrete in the built environment is another key strategy. And then finally, when it comes to carbon capture, I've already mentioned that one key technology is carbon capture and sequestration, meaning we put the CO2 underground or permanently sequester it. There's also innovation around capturing carbon and utilizing it in useful materials. So one key example in the cement industry, which is a commercial technology, is called carbon cure. Here, carbon cure uses captured carbon for curing the concrete. So all concrete, when it cures, absorbs CO2 from the atmosphere. What carbon cure does is really control the process, use captured CO2 to help cure the concrete. And by doing so, we get stronger concrete that requires less cement in the mix. But there are also companies and technologies that are looking into valorizing industrial waste by reacting them with captured CO2 to produce what's known as artificial aggregate. So if we can produce artificial aggregate, we can use it in new concrete blends and therefore both capture carbon and reduce pressure for mining. So that is the innovation landscape that we're seeing. And you can imagine that we have many emerging options that reduce emissions through different mechanisms at different places in the cement and concrete cycle. And really, to understand their full potential, we need to take a systems approach. So there are a lot of exciting innovations, but to understand which we can roll out by when and where, we need to use a whole systems analysis approach. And that's what I'll present to you next. So in my research lab, in partnership with Dr. Chow, we've developed and will soon release publicly a new model we're calling Imagine Concrete. Essentially, the model structure is what you see here. So the model considers the entire cement and concrete cycle, starting from mining, going all the way through to construction and the built environment and end-of-life concrete flows. The model tracks mass flows throughout the system. It also calculates all of the energy inputs that are required at all stage as a function of the technologies deployed. And importantly, it has an emissions layer capability as well, where we're tracking the various emissions fluxes, so positive emissions emerging from energy use and reaction emissions in the system, but also CO2 sequestration. If we can capture CO2 at the plant, if we can capture CO2 and use it for building materials, how much CO2 is taken up by the built environment. Making sure we look at the entire system and doing it in a consistent way is quite important when developing these decarbonization plans. And we've been able to incorporate more than 24 existing and emerging measures, which you see here as denoted by these little red labels. These will make sense in just a moment. An important part of the process, though, that I really want to stress is accounting for CO2 fluxes. So you might say, well, isn't that pretty straightforward? Here we have a cement kiln, it emits CO2. Isn't that the major contributor? Well, that is true. It's about 75% of all the emissions. But if we look at decarbonization, we have to take a very careful accounting of CO2 flows, because CO2 emitted from the kiln can be captured if we roll out CCS. It can be sequestered depending on the geography that's available. Is there enough geological sequestration capacity or not? Or do we take that CO2 and we turn it into useful products or use it, for example, for cement curing? When we use concrete in the built environment, how much CO2 is taken up by the built environment itself? If we think about replacing concrete with let's say cross-laminated timber, that itself is a source of carbon sequestration. We can burn it in the kiln. We can use it for carbon capture and create a negative emissions technology, or we can use biomass directly in buildings and offset concrete. The accounting for all of these CO2 fluxes turns out to be very important because they're quite significant at different places in the system. So the model that I'll present, the results I present, the key takeaway is we're always calculating the net CO2 balance, because we have in the system many positive fluxes of CO2 emissions, primarily cement production, but also all the transport, all the on-site activities and so forth that I mentioned are tracked in the model. But we also keep track of any carbon storage or any carbon sequestration that is available through the deployment of technologies, the use of mass timber. And we also keep track of the cement carbonation that's occurring in the built environment itself, which is a function of how much concrete is in place. Is that concrete exposed to the environment? How thick is that concrete? Are there surface treatments and so forth? All of this accounting is really important for realistic pathways analysis. So now I'll show you the pathways we've envisioned for China's building sector. But I want to start by acknowledging that the cement industry in China and in many parts of the world is making substantial progress. And the way to interpret these results graphs, so first of all, we're focusing on China buildings. The y-axis is the million tons of CO2 equivalents that is on net coming from the entire cement and concrete cycle for buildings. And what you see here is we're looking at scenarios out to mid-century when we get to net zero. The top line represents an artificial construct. It's a frozen scenario where in the model we say, let's assume that there is no technology progress. Clearly that's not the case, but we want to first benchmark this lower scenario, which we're calling current ambitions. The current ambition scenario aligns with the best available technologies and the policies that are already stated. So this scenario aligns with the IEA's STEP scenario. And basically what you see here is this is the expected progress that is expected to be made in China. So the difference between doing nothing and where the industry is likely to go with no further interventions gives us an idea of just how much progress the industry is expected to deliver. And it's fairly significant. So for example, for China buildings, roughly a quarter of the decarbonization is expected to already occur based on China's announced plans for efficient technologies, renewable energy policies, and so forth. However, we still have a big gap to close to get to net zero. So what I'll show you next are the remaining wedges that we've analyzed in the model. And I'm going to show you two somewhat opposing scenarios. So the first scenario just looks at the production system. This is kind of the paradigm we're in right now, where in the model, we didn't allow for any concrete demand reduction. We said, let's follow kind of the historical narrative that the decarbonization burden will fall on cement and concrete producers. How might the innovation landscape change their reliance on CCS? So this gray area is already captured by what we expect the cement and concrete industry to do already. The remaining wedges show that it is possible to get to net zero, and we knew this already, through utilizing CCS, but by considering other emerging technologies, lower carbon cement chemistries, rollout of concrete curing, mineralizing industrial waste subject to their availability, we can substantially reduce the pressure on at-plant CCS because it is behind, it is expensive, it does require new infrastructure, and it opens up new mitigation opportunities just purely from the production perspective. However, it is still quite reliant on CCS. So in this graph, you're seeing the total cumulative emissions emission savings that are associated with each of these measures. The hash shows what's expected to occur under current ambitions, and the remainder is what has to occur to get to net zero. So we're still quite heavily reliant on CCS. However, we can envision a different future. If we open up the possibility of demand side reductions and demand side changes, so can we get by with less cement in our concrete mixes? Can we get by with less concrete in the built environment? How do we do that? Well, we could consider strategies that focus on leaner construction, not only less waste at construction sites, but using just the right amount of concrete for the components and so forth, thereby reducing the amount of concrete necessary to provide structural services. We can consider substituting. Essentially, in our scenario, we're looking at cross-laminated timber subject to local potential supply constraints in China, and reduce the dependency of our future structures and buildings on concrete itself. Other strategies, improving fabrication yields, more intensive use. So this has to do with, lower floor area per capita, getting closer to, decent living standards for all, extending the lifespan of buildings, and then finally reusing components from buildings at their end of life, and limited amounts of concrete recycling above the baseline, essentially. This is a different pathway that has, frankly, no more reliance on CCS than is already predicted. You can see here that essentially the CCS wedge more or less disappeared, and we're replacing it with demand reductions. So on the right-hand side, we can see how the burden has now shifted. There's still quite a bit of burden on cement and concrete producers, but now we're able to pull on numerous other levers enabled by innovation, pulling in many other stakeholders into the decarbonization challenge with significantly less reliance on CCS, but to be honest and candid, much more reliance on demand side actions that are going to require the involvement of many new stakeholders. So what you're seeing here, it's a graphic we're still working on. I apologize if it's a bit busy, but on the left in the production centric scenario, this is the scenario where we're very heavily reliant on CCS, also reducing the amount of clinker, low carbon cement chemistries. The stakeholders involved in this transition pathway, there is some diversity here. We need cement producers, clearly. We need material scientists for new cement chemistries and carbon capture materials. We need aggregate producers, waste managers to be part of the solution. But it's limited to those with potentially, let's say, ingrained business practices and maybe financial barriers. In the whole system scenario, where we relieve the pressure on the supply side and focus much more on demand side mitigation measures, now we've enabled a whole host of new stakeholders, architects, urban planners, construction engineers, government officials, property owners, and so forth. And we can see that the decarbonization opportunity has now shifted to these stakeholders as well. This involves many more stakeholders, many more technologies, many more levers, and we see it as a narrative that is worthy of, I think, greater consideration as we look to decarbonize the cycle out to mid-century. If we can reduce the demand for materials, we can make large strides with existing technologies quite soon. That's not to say that there aren't many barriers that have to be overcome. So I'm going to wrap up just by acknowledging some of the key barriers that we've identified in our research for each of the technology classes. So shifting to either best available kiln technologies or even emerging technologies in the future has to acknowledge that basically cement plants are, they require enormous capital investments, hundreds of millions of dollars. Cement kilns have long, lifespans, 20, 30, 40 years, and so forth. Once those technologies are put in place, they're very difficult to decommission until they reach the end of their useful life. So just the stock turnover constraints we're seeing for cement kilns may pose a barrier to adopting some of those new technologies. I've already talked about shifting to low carbon fuels. It is a viable strategy. It can reduce emissions, but it is subject to low carbon fuel availability, which is quite variable around the world. And we can't replace all of our input fuels with biomass, so to speak. Clinker substitutes, we know how to do it, but often the amount of clinker that we can substitute is subject to building and materials specification barriers, perceived risk issues in end user markets and so forth. So just because it's technically feasible doesn't mean that markets are willing to accept high ratios of non-clinker materials in cement blends without the right incentives in place. Technically, it can be done, but there are market barriers to doing that. We've talked a little bit about CCS being behind. It's quite expensive. We need more incentives around the world. We need large-scale CO2 infrastructure in order to roll this out to industrial plants, and it's not happening nearly as fast as we'd like. And then we have innovations, as I mentioned, in low-carbon cement chemistries. Here, in speaking with industry experts, people who have worked in the cement industry, they see the potential for these low-carbon cement chemistries, but they point to the fact that there still will be perceived risk with those new chemistries, that there are inflexible standards in place and so forth, that it may take 1 to 2 decades before we see really substantial uptake of low-carbon cement chemistries. That's a big barrier that needs to be overcome through better incentives, better demonstrations, better pilots, and so forth. Reducing the amount of concrete in the built environment can be difficult if architects aren't on board with using less concrete, if they don't feel comfortable with switching to mass timber. Overspecification of concrete as a factor of safety is quite common and so forth. So many barriers that need to be overcome. That doesn't mean that we can't start working on operationalizing plans that move us towards net zero, but it's going to involve lots of stakeholders, lots of technology interventions, and lots of policy action to support the transition. So just to wrap up, before I turn it over to questions, yes, we can get to net zero in the global cement and concrete cycle with technologies we have in hand, and also technologies that are in the pipeline will open up new opportunities for doing so. We can get there by focusing solely on the industrial sector itself. However, that's going to require massive uptake of new kiln technologies, massive rollout of CCS and so forth. And some of those trends are not moving nearly as fast enough as they need to in order to stay on track for addressing the goals of the Paris agreements. A whole systems approach, which focuses also on demand reduction, opens up many new levers and many new opportunities for reaching net zero, potentially more quickly, potentially more cheaply, but it does involving a lot more stakeholders than we have to date. And for any of the pathways we're able to imagine when we look at combinations of these levers, many of the technologies need accelerated development, meaning they're at fairly low TRL levels or they're facing barriers with market uptake. So we need to really invest a lot more and quite soon in bringing those technologies to market, demonstrating, reducing perceived risks, putting standards in place and so forth. Otherwise, not only the demand side vision, but even the production-centric vision won't come to fruition in time to get to net zero when we need to. So there's an incredibly large policy support element to all of this as well. So with that, I'd like to finally wrap up by thanking our research sponsor. The research I just presented was funded by ClimateWorks, a nonprofit foundation in the US. So I thank them for the funding. And with that, I can turn it over for questions.
Okay. Thank you very much for your interesting presentation, and I would like to ask the audience if there are any questions.
I should mention briefly the report and the public use model should be available in the coming weeks. We're finalizing the peer review of both the report and the model now. And if anyone would like to be alerted when the model's available, if you have interest, please send me an email at the address you see on your screen.
Okay, I see some questions here on the chat. One question is, if it will be more challenging for China in the sector to meet the future carbon neutrality of 2060, any strategic suggestions about this?
Let me see. So I'll bring up the chat. I'm sorry. Okay, more challenging for China in the sector. Strategic suggestions. Well, our team and others have put together these so-called technology roadmaps for achieving net zero. It will be challenging for China. China's cement kilns are already quite efficient, among the most efficient in the world. Cement clinker to cement ratios are already quite low, among the very best in the world, and concrete demand will remain quite high. Presently, as I showed, more than half the cement in the world is produced by China, largely used in China. And even though that demand will slow down, it's still really significant out to mid-century. So, the big barriers that I see are related to how fast the technologies can be rolled out. There are plans for China which show massive amounts of carbon capture and sequestration. There are great geological resources in China for CCS, for permanent storage, but we need the infrastructure to be put in place. Demand reduction, however, is potentially large wedge for China. So my colleague Zhe Chao, who did his PhD in China and has studied the China building industry and concrete uses, likes to point out that the building lifespan in China, for example, is often quite short. So even putting in standards and incentives for extending the lifespan of buildings in China will go a long way toward reducing overall concrete demand, which helps us take a step towards decarbonization. If we don't produce that concrete in the first place, we don't have to abate the emissions. Those would be my comments there, but I agree it is quite a challenge, and 2060 seems very far away, but it's really not when we think about the long-lived assets that are already in place.
The other question, no, there are no. If we have sufficient time to realize those innovative technologies to achieve the climate target in 2050.
Yeah, I would refer. So I would refer you to the Energy Technology Perspectives 2020 report, which is publicly available, ETP 2020. It has a review of the available technologies, particularly for cement kilns, but also low carbon cement chemistries and so forth. And it gives an idea of their TRL level and when they could be available on the market, and also the status of various demonstrations and pilots. So demonstrations and pilots are really critical for accelerating the uptake of technologies. Why is that? Well, they prove them at a scale that is, reasonable. They allow companies to observe the operations and to get a sense of, does this technology work like we thought it would in the lab? What are the real world costs? What's the real world performance? So we need to invest a lot more in pilots and demonstrations in order to prove the technologies out and reduce risk, and ideally bring some of the costs down. The other thing we need a lot of pull incentives. So unless we can change, material standards, building standards, architectural practices, it'll be very difficult to change, to drastically reduce the amount of demand for concrete in the built environment, because we have a lot of ingrained design and construction practices, and also a lot of ingrained, let's say, business interests in selling more cement rather than selling less, and so forth. So by 2050, we can map out that if the technologies are available by a certain time and that they reach scale by a certain time, it is possible to get to net zero emissions. But those windows are closing quite rapidly, and I would refer you back to ETP 2020 to take a look at what does the IEA think are the critical windows for those technologies. That's the best source that I've seen to answer this question with specific data.
Okay, now the question is, any advice of what the current cement producers need to take as actions?
Yeah.
Or at least probably the question is also on how to schedule something in the future?
Yes. So, I come from the energy efficiency analysis community, and we always like to point to what we call low-hanging fruit. So for many cement plants and other types of industrial plants, there are proven low-cost, viable, efficient technologies that can be adopted today, right? So, waste heat recovery in kilns, improved efficiency in ball mills and grinding mills, and so forth. Using, reducing as much of the clinker as possible in the cement blends are really critical levers. And then using low carbon fuels if they're available, waste or biomass, that will help reduce the overall energy and carbon footprint of cement being produced today and in relatively quick order. Those are all strategies and technologies that are proven. Longer term, though, it will take investments in testing, developing low carbon cement chemistries. So there still is quite a bit of perceived risk, a lot of developments that's needed. So cement producers can help accelerate that by, testing, piloting, funding research to bring some of those low carbon cement chemistries to market, but also participating in public and private partnerships. So a lot of these pilot and demonstration plants that are being built for example, innovative kilns or CCS, companies are putting some of their own investments along with government investments into those projects, which they benefit from and also the broader industry benefits from, again, by demonstrating that a new technology is viable, understanding it, getting test data, and reducing perceived risk. So in the short term, those are the actions that I think are most important for cement producers. But in the long run, even considering carbon capture and even thinking about changing business models. So there are business models that exist in the world where companies produce both cement and concrete. Therefore, they're selling the end product to the market. And if they use less cement in the concrete, they actually can increase their profit margins. So it helps to avoid this disincentive that perhaps cement producers have for demand reduction, right? If there's demand reduction, they'll sell less cement, they'll make lower profits. It's not good for their business. But if they shift their business model to producing end user concrete products, now they have an incentive to use less cement. So that's another opportunity for the industry.
I have seen that someone has
Yeah.
uploaded something.
Yep, those are the ETP slides, and the report itself. I can give you a link to that. It's freely available. That's one of the nice things that we've seen for this report series. It used to require a fee, but now with the latest version, it's free to download. And it's probably one of the best modeling efforts that exist globally for the industrial sector. They have quite rich technology resolution in their scenarios and a lot of great technology data in the report.
Any other questions or comments from the audience? Mm-hmm. Okay, well, I think it's time to thank you very much for your speech, and well, it's a very interesting subject, as I said before, and I really think it would be very, very important to continue studying this topic, and also in the other chemical industries, also in the view of also power to fuel technologies, or power to transformations of different of CO2 also in possible renewable fuels of the future. Okay, thank you very much, Eric, and look
Yes.
forward to meeting you in person somewhere soon.
That would be great. Thank you, everyone, for attending and for the very nice questions. And do reach out if I could answer any of your questions offline. But thank you for joining me. It was a real pleasure.
Thank you. Bye-bye.
Okay, goodbye.
Thank you, Eric.
Thank you.
Bye, Ian.
Bye.
See you tomorrow, Ian. Bye-bye.